In this lesson, we're going to apply all our Python programming knowledge to do the regression and analyze the data from a 1968 American study on how drugs affect math test scores. So we're going to be writing some Python code to visualize and plot our data, and then we're going to run a linear regression to look at how well drug concentration in the tissue affects test performance. But before we do that, let's chat a little bit about the data set that we're going to be using for this exercise. I was actually genuinely surprised when I found out that research like this even exists. But then again, maybe the late 1960s were a different time in the United States. In the original research paper, the three academics by the names of Wagner, Akanjanyan, and Bing get 5 male volunteers to sit math tests after being injected with drugs. Now, I reckon the fact that these drugs were administered intravenously speaks way more for the commitment of these 5 blokes than sitting math tests voluntarily. Anyhow, the specific drug in question is called, and I hope I pronounced this right, D-lysergic acid diethylamide, or LSD-25, which Google tells me is a pretty potent hallucinogen. And the way that this experiment worked is that these 5 blokes had to give 7 blood samples after being injected with LSD. The amount of drugs that each dude was injected was actually proportional to their body weight, so that each volunteer should be roughly affected more or less equally. The blood samples were taken from the volunteers after 5 minutes, half an hour, 2 hours, 4 hours, and again after 8 hours. Now, if you remember, this is what you see in the first column of our data frame. The second column, labeled LSD_ppm, is the tissue concentration of the drug measured in parts per million. And after each blood sample was taken, the volunteers were sat down for a total of 3 minutes to solve as many arithmetic math problems as possible. And this brings me to our third column in the data frame. I've labeled this average_math_test_score. And the way these numbers are calculated is that, first off, the number shown in the column is actually the average of the 5 guys in the experiment. The second thing to note about these numbers is that the score is expressed as a percentage value, and it's not like the number of questions that they got right, but it's a percentage of the control value. In other words, the researchers knew how well people fared on average on their arithmetic tests, and they compared the performance of the volunteers against the control test scores. Another way to think about this is that if there were 10 questions and the control group got around 9 of them right, then the volunteers got about 3 or 32.9% of the questions right 240 minutes or 4 hours into the experiment. Okay, so we've imported pandas in our notebook, and then we called the read CSV function to store our data in a data frame called data. Now, we've been messing around with our data quite a bit, so if you're curious what your data frame looks like at the bottom of your notebook, then type data and press Shift-Enter. If you just started this lesson and have not run the cells above, then the Jupyter Notebook will not recognize this variable. In this case, you'll get a name error, which means you have to go to Cell and go to Run All. So that's a good thing to check if you're coming back to the Python intro after taking a break. Here we can see what our data looks like, right? We've got 3 columns, and we're going to extract each column and put it into a separate variable. The first column I'm going to extract is going to be called time, and I'm going to set it equal to data, square brackets, and then I'm going to pass in the name. I'm going to say time underscore delay underscore in underscore minutes. I'm going to hit Shift Enter and see what it looks like. If I want to know what it looks like, I can simply say print time. And here it is. Our variable called time now contains a series containing the values of the first column. Let's do the same thing with the other two columns. So I'm going to create a variable called LSD, set it equal to data, square brackets, and it was LSD underscore ppm. And the third variable I'm going to call score. I'm going to set it equal to data, square brackets, and then average math test score. I'm going to hit Shift Enter to make sure I haven't made any typos. And this gives me confidence that my Python code is working. Now we're ready to start looking at our data in a graphical way. If you recall from previous lessons, we've imported our plotting module as PLT. So we can refer to our pyplot as PLT and visualize the data in these variables. So the easiest way to do this is to type plt.plot and supply the two things that we want to see. Let's say we want to look at the time versus the amount of LSD in people's tissues. Hitting Shift Enter doesn't show me anything, and that's because we need to give our pyplot the instruction to show us the graph. So I'm going to write plt.show. And this gives me a graph that looks like this. What this plot is showing us is the amount of LSD tissue concentration over time. So we've got 8 data points and we're simply plotting a line chart. For the x-axis on this chart, we have supplied our time, and for the y-axis, we have supplied our LSD variable. Now, check this out. At the moment, our plot takes 2 arguments, right? Time and LSD. However, we're not limited to just providing these 2. We can actually provide more arguments, including an argument for the color of the graph. So I'm going to put a comma here and write color equals, and then single quotes, G. If I hit Shift Enter now, we see the line color change to green. Now, a reasonable question to ask is, how did you know that you can supply a color argument with a keyword just like this? And the answer is, I didn't know until I looked at the official documentation that's available for pyplot. Being able to read and interpret the official documentation that's available for each of these components is one of the key skills at getting good at Python programming. So check this out. We're going to head down to the part of the documentation that gives us information on the plotting method. This is the part of the documentation where we can find out more about the plotting method. We've got the name of our method up here, namely plot, and inside the parentheses, we can see it takes some arguments. Now, the documentation provides some examples as well as information about what these arguments could be. The first thing that we did was that we plotted time versus drug concentration in tissue. So we just had 2 arguments. And in the documentation, we can see that this is the way to create a plot using the default styles and colors. However, in addition to these standard X and Y arguments, we can supply some additional arguments. This is where we come across this term called KW-args. KW-args is an abbreviation for keyword arguments. And an example of a keyword argument is our color. Scrolling down, we can also see that G is a supported color abbreviation. And scrolling down even further, we can see a handy list of the keyword arguments that we can use on our plot method. So right here, we can see that color is one of these keyword arguments. But there are others too, for example, line style or line width. Let's add the line width keyword argument to our Python code now. Here's how we can do it. We'll just add a comma and then write line width equals, I don't know, say 10. Hitting Shift Enter updates the chart. And voila, we can see that now it has a very, very thick green line in it. 10 is probably a little bit too thick for my taste. I'm going to go with 3. There we go. This is not so bad. The other thing to think about with visualization and looking at data is that design is actually quite important in data visualization. Because if you think about it, the end goal is showing our data to people. And that's why we both need to make it look clear and we need to make it look pretty. Because typically, you and I are going to be in a position where we're going to have to impress both our bosses and our customers. Everybody judges a book by its cover, I'm afraid. So our chart is going to have to look a lot better than it is right now. The first thing to note is that we got to add text to our chart. We have to add labels to these axes and a title to the chart so that people know what it is they're actually looking at. The second thing is that we don't actually have to stick to the default colors. We don't have to stick to a generic green or red. We can add a custom color, and we do that by supplying a colors hex code. So here's a mini crash course in design. A hex code looks something like this. It has a little hashtag, and then it has 1, 2, 3, 4, 5 numbers or digits that come after it. In other words, a hex code is just like a particular ID for a color. Now what you'll want to do is you'll want to go to a website like, say, Flat UI Colors to grab these hex codes of colors that have already been curated for you. Because quite frankly, these colors look really, really good. So let's grab the hex code for this red, this alizarin here. And then when we go back to our plot, we can supply this hex code instead of this G. Hitting Shift Enter, I can see that now my line has been updated to this beautiful red. Another great resource to be aware of to find beautiful colors, by the way, is a website called Material Palette. If you want to include more than one color in your chart, you can click on 2 of these and you'll get an 8-color color palette that you can use in your designs. These kind of tricks are really handy for making something look beautiful really, really quickly. So let's add some text to our graph. First off, I'm going to give this graph a title. So I'm going to say plt.title, parentheses, single quotes, tissue concentration, of LSD over time. And then I'll hit Shift Enter. Excellent. But I do think that this title is a little bit small. So again, we're going to use a keyword argument to set the font size here. So the argument's name is font size. No surprises there. And I'm going to set the font size to 17. Hitting Shift Enter updates my chart. Now let's put some labels on these axes. For the x-axis, we'll write plt.xlabel, parentheses, single quotes, time in minutes, and we'll set the font size for that equal to, say, 14. Hitting Shift Enter, we can see our change right away. So now our x-axis has a nice looking label. We're going to do the same thing for our y-axis. And notice how every time we write plt, which is our object, put a dot after it, and then we're calling a method on our object. So to put that y label on there, we're going to say plt.ylabel, single quotes, tissue LSD ppm, font size equals 14. There we go. Now, these aren't the only ways of adding text to our graph, by the way. We can also add text in free form, more or less. So if you want to add a little footer to the graph, we can do that and have it display where our data came from. So let's take a look at the documentation for adding arbitrary text to our graph. Here we can see that our text method has multiple arguments that it takes. Some of these are optional, and some of these are required. The first thing you'll notice is that we have to supply an x value and a y value. These are the coordinates of where the text should be in the picture. And the second thing that you'll notice is that the S stands for string, and this is just the piece of text that should be displayed. So we have to supply coordinates for the text as well as what the text should be. Let's try this out. So coming back here, we can see plt.text. Now, I don't know exactly where the text should go. So I'm going to say x is going to be equal to 0, y is going to be equal to 0, and our string, our text itself, is going to read Wagner et al. 1968. Maybe some parentheses here as well. Let's press Shift Enter now and see where these 0, 0 coordinates actually are. Scrolling down, I can see that it places the text right here if x is equal to 0 and y is equal to 0. Let's see what happens when y is equal to, say, 5. When y is equal to 5, it moves our text up here. And when y is equal to, say, -1, I can see that it moves our text down here. So this is pretty good. We know where the origin is. We know that a positive number moves the text up, and a negative number on the y value moves the text down. I reckon that a good amount for this y value might be something like 0.5. Let's try it out. Yep, this arranges it very nicely. Now, at the moment, our font size for this piece of text is the default font size. We can set our own value again by providing the font size argument and, say, setting it to 12. There we go. Now, since we're setting the font size on a lot of things, we can also specify the font size of these numbers that are on the axes. Say we wanted the numbers on the axes to be the same font size as the label here. So I could write something like plt.xticks, parentheses, font size equals 14, and plt.yticks, parentheses, font size equals 14. If I hit Shift Enter now, we can see that the numbers now have the same size as our labels. Another thing that we can do on these axes is to set hard values for the range that they should cover. So, for example, we know that our time delay in minutes is going to be between 0 and 500. And we also know that the parts per million are going to be between 1 and, say, 6.5 or 7. To set a hard range, we can write something like plt.ylim, lim for limit, and provide two values, a lower bound, which is, say, 1, and an upper bound, which is, say, 7. Hitting Shift Enter, we can now see that our chart has updated. So it's no longer determining automatically what the range of values should be that should be displayed on the y-axis. We have now specified our own range that we'd like to show. Namely, we'd like to have the chart show the values between 1 and 7. We can do the same thing for the x-axis by writing plt.xlim and providing a lower bound of 0 and an upper bound of 500. The reason I'm trying to show all this is to get this idea across that we're kind of breaking up our Python code into two sections, if you will, for the chart. we're doing the styling, and then down here, we're actually plotting the data. And what's interesting to note about this is that the amount of code that's written to style the chart is actually getting longer and longer and longer. This is one of the reasons why matplotlib comes with something called built-in styles. These built-in styles can act as a shortcut or a template to help you reduce the amount of code that you need to write to make something look pretty. In our previous lessons, we've used the 538 style for our chart, but there's actually many other styles that you can choose from. One of the handy things to look at is actually the style gallery. And here you can see, for example, the name of the style. So the first one is called BMH, and the second one's called Classic. And the third one is called dark_background. And you can scroll down to see what these different styles translate into if you're actually going to plot a chart. Now, mind you, this is actually an unofficial style guide that I found very, very helpful. The official one looks something like this. Now, I find both of these really, really helpful in deciding what kind of template I should go with for my charts. To apply any of these particular styles to your chart, all you have to do is write plt.style.use and then provide the name of the particular template. So say we use Classic. If I hit Shift Enter, I can see my chart update. This is what it would look like using the Classic style. Of course, you can put anything you want in here. So if you wanted to use, say, dark_background, which is the name of another style, then we'll get this. I think one of the other names that I saw on the gallery was ggplot. So let me just hit Shift Enter here. Now, one thing you'll notice is that maybe the style won't be applied right away. So if you see that happen to you, just click into the cell and hit Shift Enter again. Then you should see the style applied. So I'm going to go with Classic. Now, the last thing we'll do with our plotting code is add a line of code into the cell so that our beautiful charts can be exported when we export our notebook. You see, at the moment, our charts are generated when this code is run. But if we add a percentage sign and then write matplotlib space inline, then we are telling Jupyter Notebook to export these charts along with the notebook when we go to File, Download as Notebook. In other words, this line of code here is Jupyter Notebook specific. Now it's time to run our regression.